Hi there, this is Richard Walker from Lucidate. Welcome to the 10th and final video in this series on AI for computer vision. In previous videos, we've looked at how neural networks work. We've designed, trained, and improved them, built applications for image recognition, sought improvements using convolutional filters, and developed tools to better understand, explain, and enhance their inner workings. In this video, we're going to look at video. Up until now, we've been looking at single objects in a single still frame at very low resolution. Now, we're going to look at dozens of objects in a series of full resolution moving images. This will require networks that are far bigger than those we've encountered. We'll need a larger input layer to deal with the higher resolution images. We'll have many more hidden convolutional layers to pull out all the features, patterns, and textures. But none of this will thankfully be new to us. If you look at the architecture of networks for processing video images, all of it will be very familiar. The only thing that will be significantly different is in our output layer. We now have multiple objects to consider. They can appear anywhere on the screen. We therefore need to identify each distinct object and its location. Let's spend a bit of time discussing data representation and data architecture. We can think of an image as a 3D matrix. We have X and Y coordinates. These are locations of each pixel on the screen. And the pixel values are represented in a simple 3-element vector. For a color image, we have a red, green, and a blue component for each pixel. Our input layer will read in these 3D matrices of color pixel intensity. Our hidden layers will perform the convolution and classification tasks that we're already familiar with. As discussed, there'll be more of these layers than we've currently seen, but the principles are identical. But what about our output layer? Rather than pixel intensities, we need to record what the network has identified, where it is on the screen and how big it is. The network is going to be trained to learn the mapping between pixel intensities and the positions and types of objects. We'll therefore need to label our training images with the position, size, and type of each object in every training image. To do this, we'll put a low resolution grid on the training data. We can then label each object of interest using this grid. We can say what grid cell contains the center of the object as well as its type and size. For instance, in the second row, 7th column, we have a traffic light, which is half a grid unit high and half a unit wide. Likewise, in the 5th row, 7th column, we have a person, which is 1 unit high and 1/3 of a unit wide. We can label all of the objects of interest in an image. In a couple of minutes, we'll introduce some tools that can help us do this. In this way, we can also think of our output as a 3D matrix. We have X and Y coordinates for the position on the screen. At each position, rather than a vector of red, green, and blue pixel intensities, we can instead have a vector that represents the size and type of an object detected there. We'll look at the representation of this vector shortly. When we dealt with static images, with one object per image, we used a labeling technique called one-hot encoding. This uses a vector of zeros and 1, to label unordered data. Where we label our images for training, we use a vector with zeros everywhere except in the element that identifies that object. In that sense, we have a 1. We could, of course, just label images with a unique integer, 1 for a car, 2 for a ship, 3 for a cat, etc. But one-hot encoding has many advantages for unordered data. One advantage is that after we've trained our network, the AI can assign a likelihood that it has detected that specific object. When we run a network, the output will be a vector that contains values between 0 and 1. The higher the value, the more likely the object. We can take the maximum value in this vector as our identified object, or for ensembles, we might combine the elements in multiple vectors to get a better quality estimate. This simple approach won't work for images with multiple objects, however. We need a different, richer representation to deal with multiple objects and their location. To do this, let's divide the image up into a low resolution grid. In this example, 12 by 7. Typically, you'd have more cells than that. For each grid cell, record 1. Whether the cell has the center of an object in it or not. 2. The x and y coordinates of that object. 3. The width and height of the bounding box around that object. And 4. The one hot vector used to classify the object type. On the screen, I'm showing an example of the vector used to represent the car in the lower right corner of the image. The first element indicates that there is an object in this cell without saying what type of object it is. The next two elements contain the x and y position of the center of the object in this grid cell. The next two elements contain the width and height of this object. This is the bounding box around the object. Finally, we have a one hot vector indicating that this is a car. There are plenty of free and commercial tools to help with image labeling. Here you can see an example of a commercial tool called Rect Label. To unlock all of the features, there's a fee, but the software has a free version with enough useful features for simple labeling. We will end up labeling each image with a 3D matrix, also called a rank 3 tensor. For a coarse grid with 12 columns and 7 rows, we'll have a total of 84 cells. Each of these cells will contain a vector with the bounding box and image classification data. Thus, one very useful way to think about what the neural network is doing is transforming a high-resolution 3D matrix of RGB pixel intensities into a low-resolution 3D matrix of image classification data. During training, we present the RGB images as inputs to the network, along with the corresponding classification matrix. Over the course of being shown hundreds of thousands or perhaps millions of images, the backpropagation algorithm updates the weights and biases to the convolution and classification layers. Once the network is trained, it will then produce a 3D output matrix for each frame of video that it is shown. We can query that output matrix to see which grid cells contain objects we're looking for, where the center of that object is, and the dimensions of the bounding box containing that object. Let's first look at a few example video streams to illustrate the operation of the network. After we've done this, let's take a closer look at the inputs, the outputs, and the working of the neural network. We'll use a network trained on the COCO dataset. COCO stands for Common Objects in Context. It was developed by Microsoft and is used as a common benchmark for evaluating the performance of different AI architectures for object detection. It has 91 different common objects split into 8 groups. The groups and the object types are shown on your screen. As there are a lot of animals in the COCO dataset, it makes sense to look at video footage of safaris. There's an example running on a PC with a modest NVIDIA GPU. You can see examples of these bounding boxes on the screen. They're accompanied with label information along with a measure of confidence in this estimate. This footage is running on a Raspberry Pi. I've mounted the camera to the dashboard of my car as I drive around southwest London. The Pi has a Coral TPU, or Tensor Processing Unit, to enable the Pi to get around 16 frames per second of processing. I'll show the labeling process in more detail. I'll keep this simple so that everything can fit on the screen. Instead of a 12 by 7 grid, we'll use a 5 by 3 grid for this example. And in this case, we're only interested in two types of objects, cats and ships. Here's an image of a cat and a ship. The bounding boxes have been drawn around each using rect label. We can see the cat in the bottom left and the ship in the upper right. We can then show the corresponding classification matrix. In this case, where we're only interested in two objects on a 5 by 3 grid, the size of this matrix will be 5 by 3 by 7. Most of the elements will be 0, but here you can see that in the top row, 4th column, we have the vector that identifies the ship. The first element is 1, indicating that there is an object of interest centered in this grid cell. The next two elements are the X and Y position in this cell of the center of the ship. These are followed by the width and height of the bounding box. This is followed by 0 and 1, the one hot encoding for a ship. In the bottom row, 2nd column, we can see the encoding for the cat in this image. Again, the first element of the vector is 1. There is an object of interest centered in this cell. The next 4 elements show the center and size of the bounding box. The final 2 elements are 1 and 0, which is the one hot encoding for a cat. This is an example of labeled data that will be used in training. But what would this look like as an output when the network is running and classifying images? It would be nice if all the grid cells that had no objects of interest in them were zeros, and all the objects of interest had 1 in the corresponding grid cell. But we won't get this. Instead, the cells will have vectors that will contain non-zero and non-1 numbers. We can apply a threshold to the first element in the vector for each grid cell. For values below this threshold, we'll assert that there is no object of interest in that cell. For values above that threshold, we will assert that there is an object of interest. We can get the center and size of the bounding box, as well as take the information from the one hot vector to assert what the object type is and how confident we are in our classification. In this image, we're setting a threshold of 0.6. You can see that this picks out George, Paul, Ringo and John as people. It identifies the crossing and 4 of the cars, the VW Beetle, the taxi and the car driving on the road in the background. There are many ways to describe this output: a 3-dimensional matrix, a rank 3 tensor, a matrix of vectors. They all mean the same thing. If we isolate the cell that represents John in the image and take a look at the vector in that cell, we can see how we can interact with this data to pull out the key pieces of information. The first element shows us how likely that an object of interest is centered in this cell. The value here is 0.76. This is above our selected threshold of 0.6, so we assert that there is something in this cell. The next 4 elements show us where the object is centered and how big the bounding box is. Finally, we have the one hot vector that tells us that this is a person. Our choice of threshold in the first element of the vector will determine how many objects we detect. We can see the effect of setting thresholds at different levels in these 4 streams on the screen. The video is identical in each case. The stream on the top left with the highest threshold detects the smallest number of features. Compare this to the image on the bottom right. Depending on your application, you might wish to filter out more or less objects, or apply different detection thresholds to different types of object. These image processing techniques we have looked at in this video go by the names of YOLO and SSD. YOLO stands for You Only Look Once. SSD stands for Single Shot Detector. Both algorithms have much in common. a high-resolution input layer of RGB pixel intensities, and a low-resolution output layer containing object type and position information. There are some subtle differences which are too nuanced to go into a 20-minute video. What they both have in common, indeed something that all neural networks have to a large degree, is the need for huge amounts of labeled training data. Without sufficient labeled data, it is certain that AI projects will fail. As well as the capital investment in hardware, the big tech companies have access to a large labour force for producing labelled data, as well as some cunning tricks to be able to get cheap access to labelled data. While there are uses of computer vision in finance generally, and in capital markets specifically, they are niche. Authentication and KYC using facial recognition is common in retail finance. Satellite imagery can be used for trade activity that might impact equities prices. Is there an increase in shipping in Singapore? A below average number of containers at Amazon warehouses? More haulage trucks on the road than usual? People with full bags, or a peak in the number of black cabs on Oxford Street in London? Similarly, many soft and agricultural commodities are driven by weather patterns. Vision definitely has a narrow use in capital markets. But I believe it's important to look beyond that. It's important to look at what the neural network is doing. It's able to take a vast amount of unstructured data and make sense of it. The key intuition here is the transformation of a huge amount of intensity data into a very small amount of classification and position data. In the specific case of vision, we're finding structures in pixel intensity that allow us to find edges, lines, corners, shapes, and ultimately objects. We can then classify these objects as types that the network has been trained on. I hope that the message is clear. While we've focused on computer vision for the past 10 videos, this has been a means to make the concepts behind neural networks simpler to understand. At their core, these algorithms take vast amounts of high-dimensional, high-entropy, unstructured data. With the right training samples, they're able to transform that data into simple, low-dimensional, low-entropy structured information that we can more easily interpret. Capital markets generates vast amounts of data: orders, trades, prices, volumes, risk metrics, macroeconomic data, company filings. The list is endless. As we've seen, meteorological data and human activity has economic impacts. The ability to tame this data to help make better risk, compliance, allocation, underwriting, and trading decisions is critical. With ever more data being available, the firms that can understand the complex patterns and relationships in this data will dominate their chosen markets. This is the final video in this series. Many thanks for watching. You've seen the calculus that underpins neural networks and much of AI, understood how powerful simple artificial neurons can be when networked together. We've solved classification problems using simple perceptrons, applied convolutional neural nets to computer vision to extract and combine visual primitives. We've seen how we can better visualize neural networks with weight maps, feature maps, and t-SNE. Finally, we've brought all of this together to show how neural networks can classify multiple objects in real time from a video stream. I hope you found this series useful. More than that, I hope it has given you some insights into how you might deploy AI more effectively in your firm. Please feel free to contact Lucidate using any of the methods on your screen. Please feel free to contact Lucidate using any of the methods on your screen if you feel we can be of any help to you. Thanks for watching.